Right, let's get going. So hi everyone, thanks for coming. I'm Louisa and I work in the data science team. Today I'm going to talk to you today about split tickets, how we've worked on that, and kind of how we approach the problem as a big data problem. So we're going to talk through, if I can get my slides to work, a little bit about the background to the split ticket recommender, so how we fit in with the rest of the split save project. And then we'll look at how what seems to be quite a simple problem can get quite challenging quite quickly and the best things to do about it. And we'll look at also the opposite way around. So even when you think it's quite big data, what to do where there are data gaps and when it's not big enough. And then we'll talk through something that I think is particularly important, which is this myth of the black box solution. So the idea that we can just throw something into a machine learning box and hope for the best. And then a little third and a half thing is right at the end of it all, you'll probably have to rewrite everything anyway. So let's get started with the split ticket recommender. For those of you who've been at Trainline since January, you should know what split tickets are by now, but we'll go through it anyway. Basically, the premise is that you're saving money by buying 2 tickets instead of 1. So if you're going from King's Cross to Newcastle, it can normally be about £70, but you might be able to buy a ticket from King's Cross to York, and then a second one from York to Newcastle, and for lots of different reasons. It's sometimes to do with advanced tickets selling out, sometimes to do with peak off peak boundary, the time of traveling, sometimes to do with rail cards, but sometimes through the quirks of the ticketing system, you can actually save money by buying 2 tickets. So King's Cross to York, York to Newcastle is 2 separate tickets rather than 1. The only thing is that you need the ticket that you split at, so that middle station or York. In our case, your train has to stop there. So you have to physically be able to get off the train and back on. And so you're using the 2 separate tickets. You don't actually have to do it, but it has to be possible. But apart from that, what we were trying to give as a train line was exactly the same customer experience, just 2 separate tickets, which makes it cheaper. So when we were trying to build this, when we first started, we worked out, looked at what we wanted the feature to look like and the kind of things we wanted to achieve. So first of all, the most important was that we wanted it upfront in the search results. So we didn't want customers to kind of see the through price and then click in and see if they could get a cheaper one. We wanted them to be able to compare all the different prices upfront in the search results. And now, while we were doing this, there was a lot of ongoing work to make the search results faster. And so obviously us coming in and building a split ticket recommender or a split ticket system that slowed it down wasn't going to be very popular. So I think our goal was basically to add no extra time while doing this. But at the same time, we had to return 10 results per search because it's upfront in search results. We return a number of results at the same time. We have to be able to calculate the split ticket price for every single one. Now, there's a lot of different split ticket websites out there already, and a lot of them do it through what's called exhaustive search. So once a customer makes a search, it then goes and calculates every single different option, looking at the price from King's Cross to Doncaster or King's Cross to Durham, Leeds, all of the different options where your train might go, looking at every single split point upfront exhaustively to compare the prices and find out the cheapest. But even for one search, this sometimes takes a matter of minutes. And if we're trying to do this with 10 searches in one go, and the result in the end is that actually there's no cheaper prices, a customer waiting half an hour for their search results just doesn't seem to work. So we were going to have to take a different approach, which is where our recommender system comes in. Now, our recommender system basically pre-calculates the best split point for every single journey that a customer could take in batch every single day. So then when route masters are the people trying to get the prices when a customer makes a search, when they look up the prices, they will also come to us and say, where's the best place on this route to split? And we'll return a list of recommendations. We'll say maybe York's the best place based on our analysis. And then the second best place is here and the third best place. So what they can then do is, rather than have to search all the ticket prices, they can just search the split prices for York. And if it's not there, they can try a second one and third one to be able to get a split price without having to take as much time as possible. So that's the basic premise behind the recommender. Let's look into how we approached it. So the first thing I mentioned is that something that seemed quite simple, right? It's just coming up with split prices. It actually became quite complex problem, quite a big problem very quickly. So we'll take a simple train. This is the London Euston to Manchester 12:20 service. It's one of our favourite trains to try and test things out on. It's one of the most popular routes that are searched, and it's just quite a useful one for testing. So this train has 5 stops along the journey. And from those 5 stops, a customer could take 10 different journeys. So they could get on at Milton Keynes and they could get off at Stoke-on-Trent. And that is a journey that they could take. They don't care that the train starts at Euston and goes to Manchester. Their journey is just Milton Keynes to Stoke-on-Trent. And if you work it through, there are 9 other journeys, 10 in total, that a customer could take on that train. Now, out of those, as I mentioned before, you need to have an intermediate stop to be able to split your ticket. So that kind of reduces some of them, and we have 6 different journeys with intermediate stops. So this one, for example, it stops at Stoke-on-Trent and Stockport, and a customer could split their ticket at either place. So it's somewhere we need to evaluate. And out of this, there are 10 different split journeys to compare. So even with this one route, you could have a split journey that could be Milton Keynes splitting at Stoke-on-Trent to Manchester Piccadilly, that we'd have to look at the price for. And the other option is Milton Keynes splitting at Stockport and then on to Manchester Piccadilly. So there's even within a journey, there are lots of different split options to compare. And for that, we need lots of different ticket prices. For each journey, we need 3 different ticket prices. So we need Milton Keynes to Stockport, that's split 1. Stockport to Manchester Piccadilly, that's split 2. But we also need the through fare because we need to be able to compare it and make sure that the split is cheaper or not cheaper. And that's great, we can do that, making kind of reusing ticket prices along the train. It requires 10 sets of ticket prices. However, we're trying to do this over a 90-day search horizon. And ticket prices don't exactly correlate, so a ticket price isn't always a set price 30 days before. That's another problem we'll come on to. But we need different recommendations for each of the 90 days. So if you're searching 90 days before, you need a recommendation for a split price that might be different to 10 days before. So that's one train. How bad does it get? Well, there are 23,000 passenger trains a day. That's the trains that actually run with people on them. And it's not 5 stops usually. There's an average of 11 stops on each train. But actually you can have up to 49 different stops on one train. So there are trains that go from the north of Scotland down to Cornwall. There are trains that seem to chug around every single station in Wales. And they get quite big quite quickly. And if we do the maths, each train with n stops creates n times n minus 1 over 2 possible journeys. So as you said, you can go from Euston to Manchester Piccadilly on your train, but you can have lots of different journeys that happen. And if you've got a train with 11 stops, there's 55 different journeys that a customer could take. I then mentioned that actually not all of them, like you could have a split ticket on if they're a direct train. So some of them go away, but you still are left with n times n minus 1, n minus 2 over 2 different journeys. So that's still 45 different journeys with intermediate stops if you've got an 11 stop train, which is still quite big. And then it gets bigger because, as I said, for each journey, there's lots of different split points that you could compare. So you could, as I mentioned before, there's one split possibility, which is Stoke-on-Trent, or there's Stockport. And basically it's anywhere on that the train stops except the origin and destination. So again, if you've got an 11 stop train, that's 9 different split possibilities to explore. And if you pull that all together with all the different journey options and all the different split possibilities for each journey, a train with 11 stops would create 165 different split ticket options. So it gets quite big quite fast. And also, like that's with 11 stops. We've got trains with 49 stops. It's quite a lot of different possibilities. And that's half of it, but also it gets bigger because, as I mentioned, we've got ticket prices, but there's not just one ticket price. There's ticket prices for children, there's ticket prices with rail cards, there's lots of different options that we need data for. And that's with one split point. We've actually done this for 2 as well, but the maths gets too big. So we're just going to leave it at 1 for now. And finally, that's with direct trains only. So that's if a customer's journey is just one train and that's to the final destination. But a lot of customers will obviously have connecting trains. So we need to find out a way to do exactly the same thing, but for 2 trains. So it gets quite big and quite scary. So what do we do? And what would I recommend if you had a similar problem? Well, I'd try and simplify it as much as possible and strip back the basics. So what we did there was we looked at direct trains only. We didn't think about connections to start with. We looked at single journeys, not returns, so that kind of cuts out half the ticket prices. And we looked at adults only, no rail card, no children, just to strip it back to the absolute basic. And then we took our example, so we took Euston to Manchester, and we tried to write down every different possibility that could work. And then we tested. So every time we came up with a solution or our code that ran, we tested it against that train to make sure that it worked for that train. And then gradually we built up the complexity. So we added kind of tickets with advanced prices that change, or we added connections and rail cars and things like that back into it, but only once we got the basics. So it meant that we could eventually have the complexity, but knowing that our foundations were solid in the first place. So that's how to simplify things. What happens if you want to go the other way? So what happens when your data isn't actually big enough, and how does that happen? So the first thing, as I alluded to, was connecting trains. There's not actually a timetable for connecting trains. For this kind of train, if someone searched it, there's no timetable that says you have to connect from the 1454 Liverpool train, you have to connect to the 1732. There's logic, but that's done at a different end to us, and we don't have a big database full of it. We could manually create every single connection, but it would be incredibly complex, and it would end up with loads of different journeys that customers would never travel on. And you could be connecting trains that go one way back again and things like that. So we didn't really want to do this, especially because it's not unusual to see 4 different changes in one journey. So you're trying to connect 5 different trains together. Coming up with a big database for all of them would just be ridiculous. So in this case, what we did was we actually thought about what we needed. And what we needed was a list of journeys with connections that customers usually took. And we turned to the search results because we knew that that was a kind of a record of what customers are actually doing. And from that, that was our list of journeys. I mean, it wasn't comprehensive. It didn't cover every single possible connecting journey. As I say, that doesn't really exist. And we used that as our proxy. So it was kind of turning to a different data set than we thought of to try and get the information that we really needed. So that's connecting trains. Another fun missing data we had was the ticket prices. So there's no ticket price, there's no fixed ticket price for a ticket on a single day. There's a big database full of fares. This is, for example, the fares from Euston to Manchester, my favorite route. And as you can see, there's different tiers that go up and up and up. So once the £25 tickets have sold out, it will go to the next tier and the next tier and the next tier. And obviously that's kind of reflected with time, because people will buy, the further ahead you book, as we all know, the cheaper prices, but then they'll obviously go up. But there's no link between an exact search horizon, say 30 days before departure, and a price that happens. And the tiers sell out at different times. So what, if route masters were doing it, or the people looking up the ticket price data when there's a search that happens, they use an API and it will tell them the tier that is valid at the right time. But we need to make these predictions before we know the ticket prices. So we obviously can't use that API. So again, here what we did was we turned to the search results, because again, it's somebody else's information, somebody else's calculations, but it links the time and a ticket price. And obviously it's a bit different. It's not a perfect proxy, but it was something that we could use to anchor time and data, time and price when we didn't have the exact data we needed. Even with that, there are problems, because not every single journey is searched every day, and ticket prices can go up and we're not quite sure when. As I mentioned before, prices can differ. So the price could go up on one day for a train, but the next day it could shoot up in a completely different way. So it's not reliable information. I mean, this is why price prediction is a whole other topic, but we wanted something a bit more simple. As I said, we're trying to simplify it, not make it more complex. And even more sparse data is when you look at rail cards or child's data. So that's even less information that you possibly have. So it gets quite sparse, and yeah. So what did we do? As I mentioned before, we used the data we did have, and we knew our data sets and looked at where we could get the data from instead. So we didn't have connections data, but we had search data with connections information in, or we had search data with the ticket prices in, and it was something we could use. We also thought about what we could infer using the data we had. So for ticket prices, I mentioned they were quite sparse, but occasionally the ticket prices will stay the same. There are some tickets that are a flat fare, and so we know that the ticket price is going to be the same every single day of a search horizon, regardless of whether the price goes, regardless of whether we have a search or not. And there are things like that. There's also, we know the ticket price only goes up. So if there's a data gap, at least we have a range of ticket prices that it could be in. And finally, a really useful thing we did was to learn at different levels of granularity. So the best thing to do is obviously to predict a specific train, a specific search horizon, and kind of be really, really precise about that train. We know the best split point, but that's not always possible. We might not have the information at that level. So what we can then do is go, okay, we don't know about that train, but we know about all the other trains that run along exactly the same stops. What do they do? What can they tell us? And what's the best split point from those? So it's not kind of the most accurate, most perfect, but it's something that gives us information. And if we don't have that, we can then at kind of higher and higher levels of granularity to even, this train goes from Euston to Manchester, where's the best place to split? And we can come up with our list of recommendations based on that. So at least we have something to fill in the gaps. So that's that. And my final one, my final learning is that unique problems need unique solutions. So this is my kind of personal bugbear. And this is about black boxes. So I think a lot of people think that black boxes work in a way that you can send the data in. So data comes in and your results come out. A bit like my favorite film, Chicken Run, where chickens go in and pies come out. Nice, simple, easy. However, it doesn't quite work like that. The chicken pie machine in Chicken Run, sorry for you veggies and fans of chickens, but the chickens go in whole. They go into a nice machine, knows what to do, and out comes the chicken pie. Simple, easy, done. Unfortunately, data doesn't quite work this way. There is such thing as a black box machine, but in a black box machine, first of all, chickens can go in, but actually they're a bit cleverer. So you could also put a pumpkin in and expect a pumpkin pie. You could put apples in and expect an apple pie. It's not a specific chicken pie machine. However, the chickens don't go in whole, the apples don't go in whole. We have to do some pre-processing of the data first. And so we have to get the data into recognizable chunks. We have to manually basically make it so the machine knows exactly what it's looking for. So that's the step that we have to do before it goes into this machine. Eventually it will go into the machine and it will do its nice machiney bits, and out will come different pies. However, a machine doesn't, our big data machine is not the same as a chicken pie machine. It doesn't have the recipe and the process that it needs to follow every single time. It needs to learn it over time. So an apple might go in to start with, and something resembling a chicken pie with apples might come out. And you might have to say to the machine, no, keep going, try again, that's not what we want. And it'll keep trying to make pies and keep trying to make pies. Well, this is kind of the training section. And the machine will learn, hence machine learning. And eventually a chicken will go in and a nice chicken pie will come out. And you'll go, well done machine, that's what we wanted. And eventually once you've trained it, the machine can then go off. And once it gets more of the same thing, it can eventually produce it. But there's that training step that needs to happen first. So the differences are, the first bit is that a black box off-the-shelf solution in data is only one step of a larger pipeline. You can't just throw all the data in the beginning. It needs pre-processing, so you need to know exactly how, what the form of the data needs to look like before it goes in. And it has to learn to output given what its input. So it learns eventually that it needs to output a pumpkin pie given a pumpkin that goes in. Or for a more machine learning kind of aspect, it learns that given a picture of a cat, it needs to output the label cat rather than label dog. It's a kind of training process that happens in a while. But finally, it needs to be told what success looks like. You need to know what you're expecting so you can train the model and the model can learn. So that's one of the big differences. So that would be great if we could use that. However, for something like splits, even the machine learning problem or a black box solution doesn't quite work. And that's because the splits problem is quite a domain specific problem, which means that there's no similar problems with a common solution. So the good thing about the black boxes, obviously with our chicken pie machine, we can put any kind of thing in, but our problem is to make a pie. And again, with image classification, for example, our problem is to label images or it's to recognize patterns. There's lots of different black box methods that will work because you're trying to solve a similar problem. Unfortunately, splits is quite a distinct problem and there's no kind of black box that we can put it in to learn it. The second thing is, and the reason why machine learning methods are so good is because they're able to generalize, which means that when you put in lots of apples, for example, not all the apples are exactly the same, or not all the images of cats, if you're doing an image classifier, they're not all exactly the same, but the machine learns over time. It goes, I've seen something similar to this before, and so I can train it and get my result. Unfortunately, with split tickets, a train from, you know, Oxford to Paddington is quite similar to a train from Oxford to Reading. It might go along the same line, it might even run at the same time of day, but the results are different. Or you could have even a train from Oxford to Paddington, 2 trains that run at different times of day, and your result is different. So we wouldn't be able to generalize and go, okay, we've seen one of these before, we know what the split point is. We need to actually learn every single different point. So actually, rather than just the learning from machine learning, we need additional knowledge that goes in. So what do we do, and what should we take from this? Well, first thing is, we need to write down the problem that's being solved. Rather than just thinking we can throw it into a machine and it will solve it, we need to work down every single step that needs to happen. What's our input data? What's the output data? And draw a diagram of the data flow as well, so you know the different stages and what the data will look like in each step. Then you can work out what you need to calculate, what you need to combine, and where there might be extra information you can put in. So things about ticket prices, connections, rail cards, that kind of comes into the data flow at different times. And once you've done that, maybe then you can look and say, okay, what's a common solution? Is there a black box that we can use to help us get more from our data, to learn more from our data? But it's only the final step. Most of this is logic, not magic. So finally, I'll talk really quickly about an extra additional learning that I had when doing this. So it took us about a year to create this. And we're really happy when we finished. You know, it was great, we solved the problem, we managed to do it. However, the job took 4 hours to run every single day. And we had big, large intermediate files that were output and saved, which built up to lots of AWS costs for storage, for running. And Dan Taylor, who was responsible for reducing the data cost, the AWS cost in data, was quite upset every time we backfilled more data, as it was costing quite a lot of money and we were basically throwing money out of the window. So my final learning is that actually working code does not mean it's production ready. You've solved the problem, but it's not ready to go out and be used. So what we had to think about was, what can we change to do the same thing faster? We had lots of for loops in there. We had lots of UDFs, so functions that we'd written ourselves, which were great for solving the problem, but were taking up a lot of time and weren't going to be useful in the long run. We wanted to keep the logic the same, but we wanted to find different ways of the code to actually make it run and make it quicker. Also, we had to look at what data we no longer needed to store. So there were lots of intermediate files that were useful when we were designing the problem and trying to work out the solution, because we needed to see what was kind of happening at each step. But actually, when we're running it every single day, we don't need those intermediate steps anymore. We know that it works as we expect it to. And finally, the nuclear option, which was the hardest to take, was actually, can you rewrite it in another language? I think we've all got our favorite computing language. And I wrote most of this in Python. So to be told that actually Scala would be better for some of it was quite hard to take. But we got there, and actually in the end, it produced a much faster result. So you had to be prepared to, again, keep the logic the same, but write it in a better, more efficient way if possible. And only then is it ready to be released. So a quick summary. First of all, if it looks complicated and scary, simplify your data. If you don't have the right data or you're missing data, be creative. Where can you get it from instead? What do you know? What can you infer? And thirdly, black box learning is not your solution. It is much better to have your domain knowledge to understand the problem and then use the magic, if you want to call it that, at the end, but it's mostly logic that will help you solve the problem. And finally, be prepared to write the whole thing at the end. So that's me. Thank you very much for listening. If you've got any questions, you can find me on Slack, and please do leave feedback as well, because it'd be great to hear back. But thanks very much, and that's me.